Last episode, you spent the whole run tuning when the learning rate moves, warm up easing it in, step decay dropping it, cozy in gliding it down. All of that controls how big a step you take. This episode is about the ground you're stepping on. Because here's the thing nobody tells you when you start. The lost surface of a real network is not a bowl, it's not even close. It's a vast, lumpy, high dimensional landscape, and the place your training keeps getting stuck is almost never the bottom of a pit. It's a saddle, a mountain pass, and the difference is the whole episode. Let's name the myth out loud because it's everywhere. Training slows down because it fell into a bad local minimum. You picture a marble rolling into the wrong little valley, trapped, unable to climb out. It's a clean story, it's also in high dimensions almost never what happened. Local minima that are meaningfully worse than the global one turn out to be vanishingly rare in big networks. The thing that actually stalls you has a different shape entirely, and once you can picture it, the plateaus in your loss curve stop being mysterious. Here's the shape, a saddle point. Think of the surface between two mountains. Along the ridge, you're at a peak, but step toward either valley and you drop. At the exact center, the ground is flat in every direction. The gradient is zero, so an optimizer that only looks at the gradient thinks it has arrived. It sits there, but it hasn't arrived at a minimum. It's parked on a pass, flat under its feet, with a way down sitting just off to the side that it can't see, because the gradient at that one point genuinely is zero. So if the gradient is zero at a minimum, and zero at a saddle and zero at a maximum, how do you tell them apart? You can't from the gradient. First order information is blind here. You need the second derivative. In one dimension, that's just curvature. Positive means a cup that holds water, negative means a dome. In many dimensions, the curvature becomes a matrix, the Hessian, and the numbers that matter are its eigenvalues. Each eigenvalue is the curvature along one special direction. Read the signs of those eigenvalues, and the critical point confesses exactly what it is. The rule is short enough to memorize. All eigenvalues positive. Every direction curves up, you're in a bowl, a genuine minimum. All negative, every direction curves down, a maximum, a hilltop. Mixed signs, some positive, some negative, that's a saddle, up along some axes, down along others. On our toy surface, the minimum reads eigenvalues of positive 2.01 and positive 0.88, both up. The saddle reads positive 192 and negative 130, one up, one down. That single minus sign is the entire diagnosis. Now, the misconception that bites hardest in practice. A flat region is the same as a saddle, just stuck. Not quite, and the distinction matters for what you do about it. A flat point has eigenvalues near zero. The curvature has gone limp in some direction. There's no downhill to find, but there's also no clear up. Our flat point reads eigenvalues of positive 004 and positive 001, both barely off zero. That's a degenerate near flat plateau. Not a trap, a swamp. Momentum won't slingshot you out the way it would off a saddle because there's no negative curvature escape direction to build speed along. You need a different fix. And that's the payoff of seeing it this way. A saddle has an escape hatch built in. That negative eigenvalue is a downhill direction, and any optimizer that carries velocity will eventually drift into it and roll off. That's why plane momentum, the heavy ball from episode 7, is quietly the saddle killer. It doesn't stop just because the gradient hits zero. The flat swamp is the harder case, and it's where adaptive methods earn their keep. But you can only choose the right tool once you've named the terrain, and now you can name it from 3 numbers. So let's compute it instead of hand waving it. The file is nnsaddlegeometry.py. We define one small non-convex loss surface over 2 parameters, find 3 critical points we already know the locations of, And at each one we build the 2 by 2 Hessian, take its eigenvalues, and read off the classification. No training loop, this is pure geometry. The output is the figure you've been picturing the whole episode. First, the surface. We pick LOL001 BLU2 as a function with deliberate structure, a product term and two welds, so it actually has a minimum, a saddle, and a flat shoulder rather than the single clean bowl from the conditioning episode. Plotting it isn't the point yet, we just need it callable, and we need its analytic gradient and Hessian, which we write out by hand so there's no autograd magic to trust. Next, the gradient function. Two partial derivatives returned as a length 2 vector. We'll sanity check it at each critical point. At a true critical point, this should come back essentially 0, and printing that near 0 norm is how we prove a point is critical before we ever classify it. Then the Hessian, the heart of the file. 4 second partials arranged into a 2 by 2 matrix, curvature in W1, curvature in W2, and the two mixed terms on the off diagonal, which are equal for any smooth loss. This matrix is constant in the toy bowl from before, but here it changes from point to point, which is exactly why the same network can feel like a bowl in one spot and a pass in another. Now the classifier. We hand the Hessian to Enebdolinal Eigenvalch, the symmetric eigenvalue routine, which we use because the Hessian is symmetric. And we want real eigenvalues, not the complex ones a general solver might hand back. Then a tiny sign test. All positive is a minimum, all negative a maximum, mixed signs a saddle, and anything hugging 0 within a tolerance we flag as flat/degenerate. 4 if branches, that's the whole diagnosis. The driver ties it together. We loop the 3 known critical points, and for each one we confirm the gradient is near 0, compute the Hessian, pull its eigenvalues, classify and print a one-line verdict with the 2 eigenvalues attached. The points are ordered minimum, saddle, flat, so the printout reads top to bottom, the way the figure is labeled. Last, the figure builder. We sample the surface on a grid, draw it as a shaded 3D mesh, and drop a labeled marker at each critical point colored by its verdict. The minimum and flat point in our hero teal to cyan, the saddle in the failure magenta, because a saddle is the thing that stalls you. Each marker carries its eigenvalue pair, so the geometry and the numbers sit side by side. So a plateau in your loss curve is not a verdict, it's a question, and now you know how to ask it. Build the Hessian, read the signs. Mixed signs, momentum will get you out. All near 0, you've hit a swamp and you reach for something adaptive. But there's a deeper reason the signal goes flat that has nothing to do with the landscape and everything to do with depth. When a network gets tall enough, the gradient can shrink to almost nothing on its way back through the layers before it ever reaches the surface you're standing on. That's next, vanishing gradients when depth kills the signal.